Okay, so we're now going to look at two broad classes of mathematical model. Both of them are relatively simple, and both of them have their uses. As with any sort of mathematical model of the real world, these models are imperfect, but they are useful. So, there is kind of a fairly common saying, which is that all models are wrong, but some models are useful. And the the models that we're going to look at, the two models we're going to look at, are are quite well. One of them is absolutely wrong. It's a very strong approximation. The other is extremely useful and really is not wrong, but it requires a bit of thinking about the process of grabbing an observation. So we have to introduce the idea of an experimental space. And once one has the idea of an experimental space, there are lots of things that can then be defined over that experimental space with regard to images and their stochastic behavior, in other words, the way that they vary. And the key concept you need to to think about it is that of this experimental space. So sometimes the topic of that we're going to introduce comes under the heading of Markov random fields, but I think which is known to be quite a tricky topic. But I think that you get to MRFs if you have a proper understanding of this notion of an experimental space or observation space. Well, I want to separate observation and experimental because observation space can refer to the types of things that you're observing, whereas an experimental space has within it the concept of repeated trials. So for those of you who've done neuroscience, the use of the word trials is exactly the same. It has exactly the same implication. So let's move on. We're going to start off by looking at the simplest of structural models. So the facet model is an approach to modeling a local neighborhood of an image um, by trying to split groups of pixels in that neighborhood into little regions and then fitting some kind of model to those regions. The model could be something as simple as a linear model that describes the change in intensity as a function of positional change across the plane of the image in one direction and across the plane of the image in the other direction. And the facet model uh, is is a very handy conceptual tool to define the notion of rate of change and to figure out how you can estimate the rate of change of intensity as a function of one or more coordinates of space. So this is what we're going to start with. And there are different types of facet models. So the class of facet model we're going to look at is useful as a conceptual tool to work out the relationship between gradients and how you estimate gradients or rate of change of intensity in an image. But it is also very widely used in a technique called image interpolation. You may have come across the technique or the term bilinear interpolation for if you zoom an image to make it bigger or make an image smaller or to change the size in some way. You may have come across in a drawing package or in an image manipulation package the idea of bilinear interpolation. So the facet model basically underpins bilinear interpolation. Well, one type of facet model underlies bilinear interpolation. However, you can also use other types of facet model, whereby rather than modeling the rate of change of intensity over space by a linear function, you model the intensity variation over space using a quadratic function. In that case, what you can do is you can use that to both the localize edges and also to localize centers of regions to sub-pixel accuracy. So we're going to get a better view of that as we go into chapter, I think it's chapter 4, chapter 5. But let's start off with the bilinear facet model to begin with. So in the bilinear facet model, what we do is we assume that, so we make a very strong assumption, which is that in a local neighborhood, so let's just say that this equation corresponds to the rate of change of intensity. Oh, by the way, we've got an image, by the way, that's f as a function of m and n, and this is our actual image. Okay, now we can make this a very big large image, or we can think of this as just one local region. So let's think about this as a local region. And in that local region, we're going to assume that the intensity follows this model. So this is the model of intensity variation. Okay. All right. So this this says that we've got this term a naught, we've got this term a1, and the term a2. So the coordinates m and n are relative usually. I mean, it would be sensible to think about the coordinates relative to the center of the neighborhood. We do not need to do this, but it makes the algebra that will follow a lot easier. So in other words, what we want to do is to think about, so let's take a 3 by 3 neighborhood. And so in an image, or let's say in this 3 by 3 neighborhood, this patch, we're going to be creating a coordinate system or using a coordinate system relative to the center of this neighborhood. So this is going to be m equals 1. This is, m equals minus 1. This is m equals 0. And this will be m equals plus 1. So these are the values of m. And then we're also going to have values of n. So that should be an m. It's not that easy to see. Okay. And we also have values of n that take minus 1, 0, and plus 1. Okay, so we're doing this coordinate relative to the center of this neighborhood. Okay, so the values of m are ranging from minus 1 to 0 to 1. The values of n are ranging minus 1, 0, plus 1. Now, you can also make this neighborhood bigger, so this could be a 5 by 5 neighborhood or a 7 by 7 neighborhood. It doesn't really matter. Okay, now what we're going to do is to, so let's now look at the form of this model. Okay, so we've got this term a naught that doesn't have any dependence or isn't interacting directly with any of the coordinates, so it's a constant. We have a term a1, which is multiplying m, and we have a term a2, which is multiplying n. So these terms here can be thought of as slopes, or in other words, rates of change. So these are the slope of the bilinear facet model in this neighborhood. So it helps very much, I think, to try to find an analogy to what we're doing here. And there is a really nice analogy. Well, it's not an analogy, it's a direct extension, really. So let's move to our board, and let's remind ourselves. Oops. I have to remind myself I've got a pen with me at this today. Okay, so let's remind ourselves. Let's see. Let's remind ourselves about linear regression. don't like this color, so let's go to, so in the variable y relative to, actually, let's not use variables here. Let's use measurements because that's far more sensible in this context. So, whoops, deleted the wrong words there. Okay, so in the measurement, y relative to the measurement of x. So what do I mean by that? Okay, so what we're talking about here is having is measuring pairs of variables. So for example, x could be a spatial, or x could be a location along some kind of spatial domain. It could be a location along time. It could be any sort of variable that we're changing, and at the same time observing a second measure, a second variable y that is dependent on x. So if we collect pairs of observations, x, y, let's say we collect xy pairs, and let's say we've got 10 xy pairs, okay? Those 10 xy pairs can be dropped into this two-dimensional space. So I'm plotting them as little x's, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, one more, 10. Okay, so there are xy pairs. So there is, of course, the notion of doing the really simple thing of trying to create a model of the dependency of y with of variable y with variable x, or measurement y with measurement x. Okay, so we're varying x, let's say, and we collect observations y, and we plot them on this axis, and the x values go on that axis. Very simple. Okay, so you're all familiar, I'm sure, with the idea of fitting a straight line. So helps if one draws a straight line as an actual straight line, because the whole point is that this is an assumed deterministic model between y and x. We're describing a relationship between x and y. So what we have here is so if we do fit a straight line to these pairs of points on this scatter plot, then what we are doing is fitting a model such that the variable y, okay, is being described as related to x by this sort of relationship. So this thing here describes that that line. Okay, so y is equal to mx plus c. So m, of course, is the slope of this line, and c is, of course, the intercept of this line. So I'm sure you all remember that. It's but I'm just reminding you to make a point here. Okay, so in this situation, when we do this linear regression thing, the point of this, I mean, this makes no sense. I mean, sometimes you're taught about linear regression without saying, okay, well, what can you actually use it for? So the point about linear regression is that in fitting this straight line to this scatter plot of points, what you're doing is establishing an assumed model of the dependency of variable y on variable x, or measurement y on measurement x. how does this measurement change if I change this aspect of the system, for example. Once you've done that, then the key ability that you have is to make predictions about the value of y given unobserved values of x. So linear regression just on its own serves absolutely no purpose unless you're going to make use of that trend for a prediction. So the prediction is, okay, I have my measurements of x versus y, but now somebody asks me, well, what's the value of y if x has some other value that hasn't been observed? Okay, so for example, we will choose a value over here. And so this value, at this value of x, we haven't got an observation, but we know with confidence we can jump up to here or draw, let's say, draw a line from the x-axis up to find the intercept on that red line, and then we can simply read off the corresponding value of y. So we can use this model to make predictions. And later on, we'll see that that's exactly the situation in which we find the use of the bilinear facet model most widely, where it's known as the bilinear model for interpolation. It's effectively used if you need to resize the image. And in the process of doing that resizing, you've got to figure out what the intensity would be if you acquire measurements at points that differ from those of your camera or your source image. That's the main purpose of, well, that's it. It's the main practical application of using bilinear interpolation. However, we will also look later on at the use of the bilinear model for other purposes, such as understanding how we estimate gradients within, or rates of change of intensity within an image, using, in fact, using convolution. Okay, so the question is that if we have this image, this has actually been observed, been captured by our camera. We zoom into this little 3x3 region. We look at the pixel values because we have access to them from the image array. And we now want to fit, so it's equivalent of what we've done in the linear regression case, except now we want to fit the intensity, G, as a function of M and N. And instead of using y equals mx plus c, so now remember, m is a gradient in that standard term. But here, the term m and the term n both refer to coordinates on the two-dimensional grid. So our gradients or the slopes in the one-dimensional regression case are a1 and a2, and then the equivalent of the additive constant c from y equals mx plus c is this term here. It's the a naught term. Okay, so that's really, really simple and really, really nice. So how do we go about fitting this model? So what we want to do is to minimize the error of using this model, plugging in a value of x, and then getting a value out of y. But we test this, or we fit the model, in fact, by actually using the observations that we have. So the x and the equivalent of the x and the y values. Now in this case, the equivalent of those values are, so we've got the spatial coordinate locations, which we know they're going to be m and n, so we can simply move through those spatial locations. And we have the equivalent of the y values are the actual intensities. So if we want to minimize the error in predictions, we want to also make sure that so a prediction that's higher than the actual pixel value according to the model. So a prediction according to the model that is higher than the actual observed pixel value is penalized, but also a pixel that in the observation that is below the prediction of the of this bilinear facet model is also penalized. So to penalize these in the we both of these, the positive and negative, we square the deviation. So deviation itself, which is the term GMN minus FMN, or if you like, that's the error. That on its own goes both positive and negative. So if we only use this on its own, the positive errors could potentially cancel out the negative errors. So to make sure that we actually capture both positive and negative errors and consider both of them as bad things, what we do is we square those and then sum them up. So we can also use an average here. So we can take the sum of these square deviations and then divide by the number of pixels over a region. And that's what this MN means here. And we'll see a slightly more sophisticated way of representing summing over a region here. But we can also do this over an entire image, which I'll show you a little demonstration of later on. Okay, now FMN is an actual measurement, so it's equivalent of our Y. GMN is the prediction of our model. And so that is given by this expression here, A0 plus A1N plus A2N. And so here's the subtraction. And if we square that and then do a bit of simplification, then, so by the way, what we want to do is to minimize epsilon, which is actually the squared error. So to minimize epsilon, what we can, or to find the minimum for epsilon, we can resort to calculus. And we can therefore look for a minimum of the rate of change of error with the parameters we want to fit. In this case, the parameters we want to fit are A0, A1M, and A2N. Sorry, and A2. So, I'm sorry, they're A0, A1, and A2. Okay, so we have these three parameters. And so we can, so what I've done here is create an error vector, if you like, which has, or a gradient vector is what is the correct term for it. So this is the rate of change of epsilon with respect to one of our variables, the three variables we want to fit, or the three parameters we want to fit. The second is the rate of change of epsilon with A1, and the third is the rate of change of epsilon with A2. And we can just stack these into a little three-dimensional array. Now, this is just a compact way of writing the derivative expression. And if you go onto Blackboard, in the worked derivations folder, there is a complete run through of how you get to this expression here, which is a fairly compact way of writing the derivatives. It's kind of like, it looks a bit like a matrix equation, but it also includes this weird summation in here. But that's just a notational convenience. So, so if you go to the lecture notes and have a look, you will see how you get to that and how you can get those three equations from just simple algebra, and then pack them into this little vector matrix vector representation. Okay, now at the point at which we have the minimum, so the best fit, so the minimum error is the best fit in the least square sense, then we will find that d epsilon dA naught will be equal to 0 if we're at the right point for the best fitting value of A naught. D epsilon A1 will also be 0 if we're at the right value of A1 according to the data and the model, and the same for d epsilon A2. So we can equate we can equate each of these three things to be equal to the zero vector 0, 0, 0. And what that gives you is three simultaneous equations. And crucially, and this is why it becomes extremely important to use a centered coordinate system like this. So there are some terms which involve summations of m values and summations of n values. That falls out of the equations, as you've seen in the derivation. And what you will then find is that you get three equations that are very easily separated. Although strictly speaking, it's a simultaneous equation, the three equations just separate very easily. And so you get a closed form expression for A naught, which is this expression here. So the sum of intensities Fmn over the region that we're doing the bilinear fit in, divided by this weird looking thing down here. But this is just the number of pixels in the region. So that's not hashtag, by the way, that's number of. Okay, so this summation here, let me just make that clear. It's this thing here that simply equates to the number of pixels in the region. When you actually do work through this, you'll find that you get the summation of the value 1 by as many pixels as are in the neighborhood. So I've left that in there so you can see where this comes from. This sum of Fmn is simply the sum of intensities. And so what this A naught term is simply the average intensity in the region. Isn't that cool? Right? It's just the average intensity. So in linear regression, nobody talks about this, right? But the same thing will happen in linear regression. It's your C term is just going to be yes, it is the intercept, but it's also the average of the. Well, you need to shift you need to have a centered coordinate system to do that. But if you do that, then the C value is just going to be the average of the Y values in a linear regression problem, which is really cool. Okay, the A1 term is going to be given by the sum of again its intensities, but this time every pixel intensity is also multiplied by its own M value. So the M values, just to remind you, will be going like this, so -1, 0, +1. So effectively, every pixel in here has an M value and also an N value. But for example, because we've got 3 pixels in this row, we're going to have 3 pixels that have the same M value of -1. And we're also going to have 3 pixels that have the same M value of +1. Because we've centered the coordinate system, we're actually going to have 3 pixels here, which are not going to have any weighting at all because the M value for that in this centered coordinate system is 0. So that's another simplification to the calculation when you're actually going and working this out. And then the A2 value looks just like this, except, oh, by the way, I forgot to say that in the denominator, you have the sum of the squared values of M with no F term. And sorry, finally to A2, you have A2 is the sum of NFMN, so it's very similar to this, except instead of multiplying your intensities by the M value, you multiply them by the column coordinate. Okay, so it's very simple. So please go through the derivation in the on Blackboard. You can also try doing the same derivation on the linear regression problem, just to show that you can do it. Just work through and get the rough idea of how you go about doing this, and then you can derive the way to fit a straight line rather than simply memorizing it off or reading it off a formula sheet. So here's a very simple example. It's a very artificial example, I must say, of using the linear facet model. And so what you can see here is that we've got this is an additive intensity change that's applied to this single slice MRI image. And in order to go from the image on the left, so there's a basically additive linear trend, intensity trend. I'm writing all over the image, which is very bad form, but what can you do? Space is limited. And on the right is the result of taking the image on the left, fitting a bilinear model to it. Now you can see the slope is only going in one direction. So we actually only have one non-zero, one non-zero slope in the expression. So this is increasing in the column direction, and therefore, if we go back to our model, we see that that's the direction of increasing or change in column number, and therefore A2 has a non-zero value, but the value of A1, since there's no rate of change in that direction, the value of A1 is 0. Okay, so once you fit the fit the slope, you can then take that model, predict therefore what the background slope is, or what the additive intensity component is at each point in space. So there's where you're using the model to do a prediction, and then you subtract that predicted background intensity from this image, and that gives you this image, which is a denoise or detrended version of the image on the left. Okay, so that's the practical use of the model, as I said, is in image interpolation. But we're also going to see how to use this in performing transformations, geometric transformations on images, where there's a technique that we call interpolation. So we want to figure out or predict what values the intensity of the image will have in between the observations or the pixels that we've observed them at. So very, very useful if you want to zoom into an image, of course, because when you zoom into an image on screen, for example, you create more pixels effectively. And so you need to, given a starting image, if you want to zoom into that, you need to predict the values in between the original measured pixels. So you can create more pixels. And then we will also see that there's the other use is that once we understand that you can have this idea of fitting, taking a region of an image and assuming it conforms to some sort of particular model, you can then use that information to ask the question, well, how can I estimate the parameters of that model in a local region? In particular, I may not care about some of the terms, but I may want to know definitely about rate of change in the row direction or the column direction. When you do gradient estimation using convolutional masks, that's one of the things that you want to figure out how to do, and that is very easily done using this by using the bilinear model as a conceptual model. Okay. Next, we're going to move on to how to think about an image in a sort of a statistical way. And the key thing that we need to get to grips with is this notion of having an experimental space or a trial space over which we might repeatedly observe the same scene.